This is a symbol. We might see this symbol and think that we know that this symbol represents the number 4. But that's not the only thing that we know about this symbol. As soon as we recognize that the arrangement of pixels that we're looking at represents the concept of the number 4, we also know that the symbol that we're looking at does not represent the number 1, or 2, or 3, or 5, etc. In fact, there are an infinite number of numbers that we know that this symbol does not represent. Without even thinking about it, we implicitly know an infinite number of things about this symbol. Therefore, it must be possible for a human mind to know an infinite number of things. Or in other words, this thought experiment suggests that the human mind has an infinite capacity of knowledge. But can our capacity for knowledge truly be infinite? No, it cannot be true. And through this video, we will consider why this cannot be the case. And that's the topic of today's video: the paradox of infinite knowledge and its implications on the mind. To understand why the mind doesn't have infinite capacity, let's first explore how our understanding of the mind has evolved over time. Many Greek philosophers believed that the seat of emotions and certain aspects of the mind were located in the abdominal area, particularly the heart, liver, and intestines. Notably, Aristotle thought that the heart was the center of sensation and thought, while the brain was considered more of a cooling organ. We can trace back the origin of the phrase gut feeling or gut instinct to this philosophical tradition. Additionally, Plato's theory of forms suggests that the physical world that we perceive through our senses is not the true reality. Instead, the true reality exists in the realm of forms, which are abstract, perfect, unchanging, and eternal. The forms are the perfect versions of the concepts that we encounter in the physical world. For example, we might consider the form of a circle and the form of beauty. Consider a circle. In the physical world, every circle we draw or see is imperfect, whether it's on paper, a computer screen, or any other medium. These circles have slight flaws or deviations in them. If not from the stroke of the pencil, then from the unevenness on a molecular level of whatever the medium is. However, the form of a circle is the perfect, ideal version of a circle that exists in the realm of forms. It is perfectly round, with every point on its circumference equidistant from the center, and an infinite number of sides. This perfection is something we can only conceive of in our minds, not perceive with our senses. Similarly, when we think about beauty, we see beautiful things: flowers, people, art, but each of these has flaws or is beautiful in different ways. The form of beauty, according to Plato, is the pure essence of beauty itself. It is what makes beautiful things beautiful, and it exists independently of any particular object that is beautiful. The filter/transmission hypothesis is often attributed to the prolific psychologist William James in the late 1800s. The idea is that the brain acts as a filter, limiting or constraining a broader consciousness to produce the individual experience that we have. Under this theory, the brain doesn't generate consciousness, but rather receives it like a signal, and filters or channels it like an antenna. Under this perspective, the brain can be thought of much like the antenna of a TV. Your favorite shows on your TV aren't originating within the TV itself. It comes from a signal that is broadcasted through the air, and the antenna tunes into it and converts it into a usable form. The filter/transmission hypothesis suggests that consciousness works in a similar way. The brain doesn't create consciousness, but tunes into it from a broader and potentially infinite source. The idea has been contemplated by thinkers like Aldous Huxley in order to explain psychedelic phenomena. Huxley thought that taking psychoactive drugs,
smoke weed every day,
could partly remove this filter, exposing the user to a vast collective consciousness that he referred to as the mind at large. This could explain why it is that people on hallucinogenic drugs sometimes report having shared experiences, where multiple people in a group experience the same hallucinogenic visions independently. Of course, the theories we've discussed so far suffer from some massive scientific problems. A complete lack of both a materialistic explanation and a practical or theoretical test. Any true scientific theory should have both of these. This is a huge issue because if we can't test it or flesh it out through a material mechanism, then how can we ever verify if this theory is true? Ancient philosophers like Plato and Aristotle laid the groundwork for thinking about the mind, and their ideas lent themselves very closely to the filter/transmission hypothesis. However, modern science has taken these ideas further, leading to new theories, in particular the computational theory of mind. Nowadays, we tend to look at the brain's function as computational. It is far more common to view the brain as a computer of sorts. This perspective has radically shaped our understanding of neuroscience, and has even accelerated the technological progress of computers. This perspective has grown progressively more popular since the 1940s and was subscribed to by influential thinkers like Claude Shannon and John von Neumann. This computational theory of mind answers many questions about the mind. One of the key questions is, does the human mind have infinite capacity? As you may recall from earlier with our thought experiment of the number 4, there is an argument to be made that we do have an infinite capacity. However, if our brain is a computer, we most certainly do not. However, we know scientifically that there are a finite number of connectors in the dendrites of neurons, and there are a finite number of neurons in the brain. On average, a neuron has around 7,000 synaptic connections to other neurons. These connections are primarily formed on the dendrites. There are roughly 86 billion neurons in the average brain. Thus, we can estimate the number of possible neuronal connections to be 7,000 connections per neuron times 86 billion neurons to be about equal to 602 trillion possible neuronal connections. However, this assumes that every neuron can connect to every other neuron, which is not the case. We know that these connections are going to be limited by proximity. Some neurons may not be able to connect to other neurons if they are too far away from each other, and specialization. We do know that certain sections of the brain serve different specialized functions. That is to say that there are certain groups of neurons that fire together for specific functions and don't necessarily need to connect to every other neuron. As such, we might revise our estimate more conservatively that the number of neuronal connections is probably closer to around 100 trillion connections. This is a very large number, but it is not infinite. This means that there must be a finite limit on the number of possible neuronal connections that we can use to represent memories, thoughts, feelings, and behaviors. Therefore, we cannot physically have infinite capacity. This lack of infinite capacity has implications on the number 4 thought experiment. Physically, we cannot have infinite knowledge. While the number of neural connections we can have is staggeringly large, it is not infinite. Well, if we can't be said to know an infinite number of things about the number 4 because they derive from abstract relationships, then wouldn't we also not know the number 4, since we define it based on its abstract relationships? So how does it actually work? Do we or do we not know what the number 4 is? Well, what we know is a finite set of generalized relationships that just so happen to be applicable to an infinite number of numbers, including the number 4. In our base 10 number system, we use the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Then when we reach the end of our 10 numbers, we proceed by adding 1 to the next digit to the left, and looping our rightmost digit back to 0. We use these abstract rules and principles because they can be usefully applied to help us conceptualize and categorize infinite numbers. But there are other number systems that use different bases. For example, binary code implements a base 2 number system, where each digit is either a 0 or a 1. If you know that each digit of binary represents a power of 2, you can use this base 2 number system to represent any number. Now, imagine a number system where every possible number has its own unique symbol, so you never need to implement any new digits or rules that govern them. This type of number system would be effectively a number system in base infinity. If we truly understood each number conceptually, then we would have no need to rely on general rules like we find in our base 10 number system. We would be able to comprehend a number system in base infinity, where each number is represented with a unique symbol, rather than a system of digits that we use in base 10. In base infinity, we would need infinite unique symbols. We wouldn't have any use for systematic rules like digits. And yet, our brains only have a finite number of neural connections that can symbolize each number. Mapping each number onto our neural connections would be like trying to store an infinite amount of data on a finite number of USB drives. There's just not enough memory. It's just not physically possible. This highlights a crucial distinction. We don't explicitly know an infinite number of things. Instead, we understand a finite set of general principles that we can apply to an infinite number of things. For an analogy, learning a number system is kind of like learning a language. Learning a language is like learning a set of rules for combining words. You don't memorize every possible sentence. You just learn general principles like grammar and vocabulary, which let you understand and create countless sentences. Similarly, our brain uses finite rules to navigate the infinite possibilities of numbers. If we did have an infinite capacity, then the computational theory of mind would have difficulty explaining it. But the filter/transmission hypothesis could simply explain this away by proposing that the mind at large, as proposed by Huxley, would be infinite. Perhaps they would explain this by saying that if the signals that our mind filters are transmitted from the realm of Platonic forms, and the Platonic forms are infinite, then an infinite number of unique symbols to constitute a true base infinity number system could exist within this Platonic plane. But the reality is that we don't have infinite capacity, so the computational theory of mind is still viable. However, the fact that we don't have infinite capacity doesn't eliminate the transmission/filter hypothesis entirely. The filter hypothesis can simply argue that the reason why we can't understand a base infinity number system is because our brains are filtering out that part of the mind at large. At the end of the day, it is the lack of any materialistic explanation or practical or theoretical test that really elucidates why the computational theory of mind is a preferable explanation. The thought experiment of the number 4 reveals a crucial insight. The human mind, though extraordinary in its capabilities, operates within the bounds of its physical limitations. We do not possess infinite knowledge. Rather, we wield a finite set of principles that allow us to comprehend and interact with the infinite complexity of the world around us.